Hello everyone, very good afternoon. Kindly confirm if audio video is clear. Very good afternoon everybody. Please confirm if audio video is clear. If everything is okay, then we can start the session. Uh, Glitch. Just 1 minute. Yes. Okay. So I believe everything is fine. So let's begin the session. This is the third lecture of set theory and algebra. In the last two sessions, we have already discussed the concept of sets. We know that what is a set, etc. Everything we have discussed. Apart from that, in the last class, we have understood the concept of set operations and the properties of set operations and Cartesian product, and we have defined different types of relations. Among those different types of relations, we have already covered some of the types of relation, but some are still remaining. So we'll complete those relations, and apart from that, we will discuss the concept of equivalence relation, partition of a set, and in between there's a thing which is called equivalence class. So I hope you guys are regular, because if you are regular, then you know that in the last class we have started with the different types of relations. We were able to cover these three relations, that is diagonal relation, reflexive relation, and irreflexive relation. We still need to cover this 7 more types of relation. So first we will cover this 7 different types of relations which are pending from the last class. Then we'll start the discussion of equivalence relation, equivalence class, and partition of a set. Clear? So let's begin. So diagonal relation, I hope you understand that if A is a set and 1, 2, 3 are the elements, then the diagonal relation on set A is nothing but a relation that contains all the diagonal order pairs with respect to set. Yeah. Now, if we talk about reflexive relation, then reflexive relation is nothing but if we have a set 1, 2, 3, then reflexive relation, what's a reflexive relation will be will eventually cover all the diagonal order pairs. So that will be 1, 1, 2, 2, 3, 3. All the diagonal order pairs must be present, and apart from that, you can union with set of any combination. We have already discussed this, so don't worry about my writing here. So set of any combination of non-diagonal order pairs. What's the logic? That apart from all the diagonal order pairs must be present, and apart from that, there can be any combination. Very good evening, 𝐂𝐤𝐴. Now, next one is irreflexive relation. So, irreflexive relation is what? Sir, a relation. None of the diagonal order pair should be present. None of the diagonal order pair should be present. If none of the diagonal order pair is present, then apart from that, there can be any combination of non-diagonal order pairs. Clear? So, this three we have already discussed. Let's begin with the symmetric relation. What do we mean? Sir, the name symmetric itself suggests something. But anyway, before we start the discussion, I believe to explain the concept, I'll require that A cross A, so that you will understand the things that is about number of relations in more detail. Let's assume A is a set which contains 1, 2, 4 up to n elements. Then what did we say? The Cartesian product A cross A will be set of all order pairs from A to A. That is, one will relate with 1, one will relate with 2, one will relate with 3, so on. One will relate with n. Similarly, 2, 1 will relate with 1, 2 will relate with 3, so on. 2 will relate with n also. 3 will relate with 1. 3 will, and so on. And similarly, up to n, n will relate with 1, n will relate, n will relate with, and so this whole set will eventually define the Cartesian product A cross A. Clear? Okay, so these are the things. Sir, yesterday we defined certain things that these are called diagonal order pairs. Sir, how many diagonal order pairs are there? Sir, exactly n diagonal order pairs will be there if the size of the set is A cross A. Apart from that, all these order pairs, whatever, right, they are called non-diagonal order pairs. Exactly how many non-diagonal order pairs are there? Sir, overall number of pairs, So if I say the size of A cross A is n square. So out of this n square order pairs, exactly n order pairs are diagonal order pairs. Remaining n square minus n will be non-diagonal order pairs. That's what we have already covered in the last class, but to explain the concept, I need this diagram. Therefore, I created this once again. Don't worry about that. Yeah, so nothing, don't know. Okay, so let's begin the session. Sir, what do we mean by symmetric relation? Symmetric, sir, the name itself suggests that there should be some symmetricity, right? So with respect to order pair, what will be symmetricity? Let's try to understand. A relation R on set A is called, there is a symmetric relation only if, so only if what condition is satisfied? Only if certain condition is satisfied. What? That if an order pair A comma B, or whatever you want to call it, x comma y, if order pair x comma y belongs to R, that is if x relates to y with respect to relation R, if x comma y belongs to R, then sir, xy, what will be the symmetric order pair with respect to xy? So the symmetric order pair with respect to xy will be yx, then y comma x should belong to R. Yeah? That is, if x relates to y, then y should relate with x for all xy belonging to set A, for all xy belonging to set A. Sir, please, this is an if condition. If condition means what? Sir, we need to worry about this then condition only if condition is true. That is, if x comma y itself is not present in the relation, then you don't need to worry about y comma x. I mean, it's not needed. Clear? So I hope you understand that if then condition says that if condition is true, then only then condition must be true. If condition itself is false, then we don't worry about then condition, that if then statement will be considered as true. So for all x comma y belonging to set A, this statement should be true. That means for whichever x comma y, this if condition is satisfied, for those x comma y, then condition should also be satisfied. If there are some elements or some pair of elements for which if condition itself is false, then for them we don't need to worry about then condition, for all will still return true. For all will still return true. Clear? So anyway, let's try to understand with the help of example. So let's take this. Sir, first of all, A is a set, whatever the set is. Now my question is, if I take empty relation, will it be symmetric relation? Please tell me. Will it be symmetric relation? So what is the condition? Sir, if condition satisfies, then only we need to worry about then condition. If for none of the pair of elements, if condition is satisfied, then we don't need to worry about then condition for any of the pair of element. For all will still return true. That is with respect to this empty set, it is the smallest symmetric relation on set A. The smallest symmetric relation on set A. Sir, apart from that, sir, what if some of the diagonal order pairs are present? So the idea is, if diagonal order pairs are present, we don't need to worry about anything, because if x comma y is present, then the same one will behave as y and same one will behave as x. So if x comma y is present, then y comma x is also present, because it is a diagonal order pair and both x and y are same, x equals to y. If x equals to y, then x comma y will be same as y comma x. You don't need to worry about anything. So because of presence of diagonal order pair, there will be no problem in the symmetric relation. But if we have any non-diagonal order pair, let's assume if we have 1, 2, then x comma y, that is 1 relates to 2. Therefore, 2 should also relate with 1 in the relation R. So, if 1 comma 2 belongs to relation, then 2 comma 1 should also belong to relation. So, please tell me whether this relation is symmetric relation or not. Yes, sir, it is a symmetric relation. Yes. Okay. Let's look at the third one. Now, sir, my question is that please let's assume that some of the diagonal order pairs are present and there is no problem because of diagonal order pairs. Now, the problem is if this 1 comma 3 is present, then for symmetric property 3 comma 1 should also be present. So, for 1 comma 1 symmetric property is satisfied. For 2 comma 2 symmetric property is satisfied. For 1 comma 3, 3 comma 1 is present. Similarly, for 3 comma 1, 1 comma 3 is present. So, as of now, there is no problem. As of now, there is no problem. But the moment I add something like 2 comma 3 and I complete the relation. So, 1 comma 1 is okay. 1 comma 1 is okay, 2 comma 2 is okay, 1 comma 3 is okay, 3 comma 1 is okay, but this 2 comma 3 is not okay, and we said that this property should be true for all pair of elements of set A. But for one pair of element, that is for 2 and 3, this property is not satisfied. This property is not satisfied. Therefore, what can we say? Sir, 3 comma 2 does not belong to R3. With respect to relation R3, if 2 comma 3 belongs to relation R3, then 3 comma 2 should also belong to relation R3. But in this case, 3 comma 2 does not belong to relation R3. Therefore, not symmetric. Clear? Okay, sir. Now, the next question that I would like to ask is, let mod A equals to n, then number of symmetric relations on set A Anybody wants to give the answer? If mod A equals to n, then how many symmetric relations are possible on set A? That's the question. Okay, so let's look at this. To answer this question, we must focus at this particular thing. So what's the idea? The simple thing is, sir, because of presence or absence of diagonal order pair, there will be no problem. So what's the idea, sir? There can be any number of diagonal order pair. There can be any number of diagonal order pair in the symmetric relation. So the thing is that for those n diagonal order pairs, we have 2 raised power n choices. They may be present or absent, it does not matter. Okay. For n diagonal order pairs, there is no problem. They may be present and they may be absent. But what happens with respect to non-diagonal order pair? Sir, with respect to non-diagonal order pair, if 1 comma 2 is present, come on, look at this. Sir, if 1 comma 2 is present, then 2 comma 1 should also be present. If 2 comma 3 is present, then 3 comma 2 should also be present. If 1 comma 3 is present, then 3 comma 1 should also be present. That is, either both of them will be present in the relation or none of them will be present in the relation? Both of them, 1, 2, 2, 1, both of them will be present, or neither 1, 2 will be present, nor 2, 1 will be present. So let me define a new terminology that these are the non-diagonal order pairs. Now, this individual thing can be seen as a symmetric pairs of non-diagonal order pairs, symmetric pairs. So these are the symmetric pairs of non-diagonal order pairs. So this two things will make a pair and these two are symmetric. So symmetric pairs of non-diagonal order pairs. How many symmetric pairs are there of non-diagonal order pairs? Sir, number of symmetric pairs will be, sir, overall non-diagonal order pairs are n square minus n. Overall non-diagonal order pairs are n square minus n. They will be combined, or ultimately 1, 2 and 2, 1 will be combined in a single symmetric pair of non-diagonal order pair. 1, 3 and 3, 1 will be combined into a single symmetric pair of non-diagonal order pair. So there will be n square minus n by 2 symmetric pairs of non-diagonal order pairs. Clear? Now the idea is, sir, how many symmetric relations are there? So number of symmetric relations. Sir, we need to look for diagonal order pair as well as non-diagonal order pair. So with respect to diagonal order pair, for n diagonal order pair, any combination of diagonal order pair is allowed. That is, there are 2 raised power n choices. And for n square minus n by 2 symmetric pairs of non-diagonal order pairs, either the symmetric pair may be present, or the symmetric pair of non-diagonal order pair may be present, or symmetric pair of non-diagonal order pair may not be present. So again, there are 2 choices for each one of those n square minus n by 2 symmetric pairs of non-diagonal order pairs. So this will be the number of symmetric relations. So it will become 2 raised power n plus n square minus n by 2. If you solve this, it will become 2 raised power n square plus n by 2. Clear? So these are the number of symmetric relations on set A. Clear? Let's move to the next type of relation, that is antisymmetric relation. That is antisymmetric relation. Sir, it is not asymmetric. It is not asymmetric. Please mind it. Symmetric says that if x comma y is present, then y comma x should be present for all the cases. If x comma y is present, then y comma x should be present for all the cases. But what happens with antisymmetric relation? Antisymmetric relation says, let's try to understand the definition. A relation R on set A antisymmetric relation is antisymmetric relation only if certain condition is satisfied. What condition is satisfied? Only if look at this, if x relates to y, if it is the case that x relates to y and y relates to x, that is, if both x relates to y and y relates to x, then what should be true? Then it says that it should only happen if x relates to y and y relates to x, then x must be equals to y for all x comma y belonging to, for all x comma y belonging to set A. That is if x comma y belong to R and y comma x also belong to R, then it should happen only when x is equals to y for all x comma y belonging to set A. Now, sir, what does it say? So the meaning of this definition is that if at all it is the situation that both x comma y and y comma x are present, then the case is that x should be equals to y. That is, diagonal order pairs are allowed. That is, diagonal order pairs are allowed. But apart from apart from diagonal order pairs, if x is x comma y and y comma x, then x must be equals to 5. So the idea is, sir, if 2 comma 3 belongs to R and 3 comma 2 belongs to R, so if condition is true, that x comma y belongs to R and y comma x belongs to R, then for this statement to be true, this x should be equals to y, that is 2 should be equals to 3, but it is false. So that is, when if condition is true, if then a statement becomes false. When if condition is true, if then a statement becomes false for any of the order pair, then the whole statement will become false and for all will start returning false. But this for all should return true. So what's the constraint? Sir, either the order pair should be diagonal order pair, or if it is not the diagonal order pair, then the if condition itself should be false. If condition itself should be false means it should not happen that both x comma y and y comma x belongs to R. Either x comma y should belong to R and y comma x should not belong to R. So because of this and, this is false, so this and will return false. If x comma y itself does not belong to R, then this is false, so and will return false. So that's the idea. Clear? Okay. So what does it mean? That diagonal order pairs are perfectly fine with respect to antisymmetric relation, but for non-diagonal order pairs, if whatever order pair a comma b is present in the relation where a is not equals to b, then b comma a should never be present in the relation. Otherwise, this if then statement will become false and for all will return false. Yeah. So okay, let's look at the example. Let a equals to 1, 2, 3. Again, please try to understand, apart from reflexive relation and diagonal relation, this empty relation will be irreflexive, symmetric, antisymmetric, asymmetric, transitive, everything. Yeah. Forget about equivalence and partial order. We are not there yet. But anyway, so this empty relation will not be a reflexive relation on a non-empty set. It will not be a diagonal relation on a non-empty set. Apart from that, it will satisfy all other properties. So is the smallest anti-symmetric relation. Okay, sir. R1 is fine. Let's give another example. If I write 1 comma 1 and if I write 2 comma 2 also, if I write 1 comma 2, if I write 3 comma 1, is it a antisymmetric relation? Okay. Is it an antisymmetric relation? Sir, diagonal order pairs are allowed, no problem. Diagonal order pairs are allowed, no problem. 1 comma 2 is present, 2 comma 1 does not belong to R2, therefore no problem. Why? Because if x comma y belong to R, then y comma x should not belong to R, as long as x is not equals to y. So 1 comma 2 is present and 2 comma 1 is not present, so it's perfectly fine. Similarly, here, so 3 comma 1 is present, but 1 comma 3 is not present. Therefore, no problem. So none of the order pair of the relation R2, none of the order pair of relation R2 creates any problem. Therefore, anti-symmetric relation. Okay. Then what? Let's look at the third example. Same, set is same. Want to make it complicated? R3. So if I write something like, so 1, 2 is present, 3, 1 is present. Is it an anti-symmetric relation? Yes, sir. Diagonal order pair may be present, may not be present. There is no problem. 1 comma 2 is present, so 2 comma 1 should not be present. 2 comma 1 is not present, so it is okay with respect to 1 comma 2. 3 comma 1 is present, so 1 comma 3 should not be present. 1 comma 3 is not present, so it is okay with respect to 3 comma 1 also. So none of the order pair is creating any problem with respect to anti-symmetric property. Therefore, anti-symmetric relation. Clear? Now, R4, let's look at this. Sir, I have 1 comma 2, don't have 3 comma 3 comma 1, don't have 1 comma 3. 2 comma 3, don't have 3 comma 2. But let's assume if I have something like what? Sir, okay, there will not be anything else, not possible. So let's do one thing, that we have this 2, we have this 2, but we have 2 3 as well as 3 2. 2 3 as well as 3 2. So what will happen? Sir, 1 comma 2 is present, so 2 comma 1 should not be present. It's absolutely fine. 3 comma 1 is present, so 1 comma 3 should not be present. It's absolutely fine. 2 comma 3 is present as well as both. So what do we know? Sir, you can actually see one thing, that 2 comma 3 belongs to R4 and 3 comma 2 belongs to R4, but 3 but 2 is not equals to 3, therefore not anti-symmetric. Because in an anti-symmetric relation, if x comma y belongs to R and y comma x belongs to R, then x and y should be equal. But in this case, these two are present, but x is not equals to y. Therefore, okay. So therefore, it is not an anti-symmetric relation. Okay, sir. Let's try to find out the number of anti-symmetric. Let mod A equals to n, then number of anti-symmetric relations. Number of on A will be equals to. So again, you need to understand one basic thing. That's there is no restriction on the diagonal order pair. So any number of diagonal order pair may be present or absent out of n diagonal order pairs. So again, with respect to diagonal order pairs, we will have 2 raised power n choices. But here comes an important thing with respect to non-diagonal order pair. So let's assume if we look at the pairs, sir, overall, this is very tricky. I mean, I don't know. Sir, if I take two elements, x and y, I'm not saying order pair. If I take two element x and y such that x is not equals to y, such that x is not equals to y. So if I create any order pair of x and y, it will be a non-diagonal order pair. If I create any order pair of x and y, then it will be a non-diagonal order pair. So with respect to element x and y, what are the things which are allowed in an anti-symmetric relation? So the things which are allowed is that x comma y is present in the relation, but y comma x is not present in the relation. So this is case 1, this is allowed. X comma y is present and y comma x is not present, so it's perfectly fine. Similarly, y comma x is present, but x comma y is not present. So it's okay. If both are present, then only x should be equals to y. If one is present, another is not present, there will be no problem. So this is also allowed. Right? One more case is that neither x comma y is present nor, come on, go, nor y comma x is. So neither x comma y is present nor y comma x is present. So this is also allowed, because if both of them are present, then condition should be true. If any one of these two or none of them is present, is perfectly fine. It is also allowed. But with respect to order pairs of x and y, there are 4 choices, that one is present, another is not present. 2 cases, x comma y is present, y comma x is not present. Y comma x is present, s comma y is not present. None of those 2 are present. But one case is that x comma y is present as well as y comma x is. If both of them are present, then it is not allowed in symmetric relation. It is not allowed in symmetric relation. Now, my question is, sir, out of n elements, in how many ways we can choose two distinct elements? Distinct, not seen. Some out of n element, two distinct elements can be chosen in NC2 ways. Out of n elements, two distinct elements can be chosen in NC2 ways. And for every pair of distinct elements, there are three combinations which are allowed. That is, for every pair of distinct elements, there are three choices. Therefore, it will become 3 raised power NC2. So it will become 2 raised power n into 3 raised power. So NC2 is nothing but n into n minus 1 by 2. That is n square minus n by 2. That is n square minus n by 2. So this is the final answer. I don't know how many of you are able to follow this, but there's a very tricky thing. Please, if x and y are two distinct elements, then only they will create non-diagonal order pairs. Now, if x and y are two distinct elements, then for two distinct elements, what are the different possibilities which are allowed in an antisymmetric relation? Sir, x comma y is present but y comma x is not present. Y comma x is present but x comma y is not present. Neither x comma y is present nor y comma x is present. So three are the possible cases for two distinct elements, but one case is not allowed. Overall there are four cases. So for two distinct elements, three cases are allowed, one is not allowed. So it will become n square minus for NC2 elements, for NC2 pair of distinct elements, each pair of distinct element has three choices. Therefore, overall number of combination will be 3 raised power NC2. So that's your answer for number of antisymmetric relations. Now go back to the definition of symmetric and antisymmetric. So when we said symmetric, we said if x comma y belongs to R, then y comma x should also belong to R. Now, in antisymmetric, we said that it's possible for x comma y and y comma x to be present in the same relation, but it is allowed only when x is equals to y. That is, diagonal order pairs are allowed. But for non-diagonal order pairs, if x comma y is present, then y comma x should not be present. If x and y are distinct, then if x comma y is present, then y comma x should not be present. Then, sir, what is asymmetric? Asymmetric is actually asymmetric. That is, if x comma y is present, then y comma x should not be present, no matter whether x equals to y or not. So, what will be the definition for asymmetric relation? It will be a relation R on set A is asymmetric relation only if what is the condition? Only if x relates to y, then y should not relate with x for all x comma y belonging. So what does it mean? It says that is, if x comma y belong to R, then for any such x comma y, y comma x should not belong to R for all x comma y. Okay, so it's a general definition, that is, so it's a general definition, that is, if x comma y belongs to R, then y comma x should not belong to R even if x is equals to y. So it says that is, diagonal order pairs are not allowed. Why? Because if we say 1 comma 1 belongs to R, then this is x and y, and at the same time it is y and x. So if x comma y belongs to R, then y comma x will also belong to R if it is a diagonal order pair. If it is a diagonal order pair, then if x comma y belong to R, then y comma x will also belong to R. But we are saying if x comma y belong to R, then y comma x should not belong to R, no matter whether x is equals to y or not. So therefore, that is, diagonal order pairs are not allowed. Diagonal order pairs are not allowed. Apart from that, if a non-diagonal order pair x comma y is present, then y comma x should not be present. Similarly, if y comma x is present, x comma y should not be present. Okay, sir. So let me first do the example of asymmetric relation. We'll talk about number of asymmetric. Equals to 1 to 3. Okay, sir. So, with the very first relation is empty relation. Is smallest asymmetric relation. Okay. Second R2. Sir, let's assume 1, 1. So, is it asymmetric? No, sir. No, 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 no. Diagonal order pairs are not allowed. Not allowed. Therefore, not an asymmetric. Okay, let's look at some more. Let's assume R1, R2, R3. 1, 2 is present, 2, 1 is not present. 3, 1 is present, 1, 3 is not present. But if any, again, same reason, again I can say same reason. Diagonal order pair is not allowed, therefore not asymmetric. Then what will happen? So the idea is that none of the diagonal order pair should be present. None of the diagonal order pair should be present. None of the diagonal order pair should be present. And if any non-diagonal order pair is present, then its symmetric pair should not be present. So 1, 2 is present, then 2, 1 should not be present. So 3, 1 is present, then 1, 3 should not be present. So 2, 3 is present, then 3, 2 should not be present. So 1, 2 is present, 2, 1 is not present. So is it okay to have this in the asymmetric relation? Yes, sir. 3, 1 is present, 1, 3 is not present. So it is also okay. 2, 3 is present, 3, 2 is not present. So it is also okay. Yes, sir. All of them are satisfying the condition. Therefore, asymmetric relation. Let's move to the next one. Sir, R5. Sir, it's okay that if any of the diagonal order pair is present, then it will not be asymmetric. But if none of the diagonal order pair is present, then will it always be symmetric? Will it always be asymmetric? Let's check. Sir, 1, 2, 3, 1, 2, 3, 2. So this is symmetric. This is asymmetric or not? This is asymmetric or not? So 1, 2 is present and 2, 1 is not present. So it's fine. 3, 1 is present. 1, 3 is not present. So it's fine. So 3, 2 and 2, 3 both are present. Therefore, not asymmetric. So it's not only with respect to diagonal order pairs, but with respect to non-diagonal order pairs also. If x, y and y, x both are present, then it will not be a asymmetric relation. It will not be an asymmetric relation. If any of the diagonal order pair is present, boom, it will not be an asymmetric relation. But there are some relations which may be asymmetric. Anyway, so there are many other things which does, but that's okay. Let mod A equals to n. Then my question is, how many asymmetric relations are possible? Then number of asymmetric relation possible on set A will be what? Simple story. None of the diagonal order pair should be present. None of diagonal order present. Okay. And with respect to none of the diagonal order pair should be present. And with respect to non-diagonal order pair, you just need to understand it will be exactly same as antisymmetric. That non-diagonal order pairs will be made of two distinct elements of set A. Now, for two distinct elements, the condition that is for non-diagonal order pair, the condition will be exactly same as antisymmetric. That is, if x, y is present, then y, x should not be present. If y, x is present, then x, y should not be present. If both of them are not present, it's also fine. But if both of them are present, then it will be a problem. So again, for two distinct elements, there are three different pairs which are allowed, and two distinct elements can be chosen in NC2 ways. Two distinct elements can be chosen in NC2 ways. Therefore, number of asymmetric relation will be how many? Sir, out of an element, two distinct elements can be chosen in NC2 ways, and for each pair of distinct elements, there will be three choices with respect to order pair. Therefore, it will be 3 raised power NC2. So, NC0 will be 1, NC0 will be 1, gone. It will be only 3 raised power n square minus n by 2. So, with respect to asymmetric, it will be just 3 raised power n square minus n by 2. With respect to antisymmetric, it will be 2 raised power n multiplied by 3 raised power n square minus n by 2. Clear? So, these are the relation. Next one is transitive relation. Next one is transitive relation. So, what is our transitive relation? A relation, sir, transitive property we know. If A equals to B, something like that. If A equals to B and B equals to C, that is A equals to B and B equals to C, then A should be equals to C. Then A will be equals to C. So, similar, I mean, this is just to remember, not the exact same case, but this is just to remember. That's what we know about transitivity, that if A and B are equal and B and C are equal, then A will also be equals to C. So, what will be the definition? A relation R on set A is a transitive relation, only if, when? Only if X relates to Y and Y relates to Z. That is, X is related to Y and Y is related to Z. So, there is a common element Y. So, X relates to Y, Y relates to Z. Therefore, X should relate with Z. Then X should relate with Z for all X, Y, Z belonging to set A. If condition is satisfied for any X, Y, Z, then condition should also be satisfied. If condition itself is false, we don't need to worry about then condition will be true, if then statement will be true. Okay, now what does it say in belonging to? So that is, if X comma Y belongs to R and Y comma Z belongs to R, then X comma Z should also belong to R for all X, Y, Z belonging to Z. Yeah, that's the property. Now, please try to understand. It will be difficult to check whether the relation is transitive or not. I'll just give you an example. Assume equals to 1, 2, 3. So the very first thing is, sir, empty relation is the smallest transitive relation. If condition itself is false, you don't need to worry about then condition. Is smallest transitive relation. Okay. What about another relation? If I take R2, so, sir, there will be no problem because of presence of diagonal order pair. There will be no problem because of presence of diagonal order pair. Because of absence of some of the diagonal order pair, there may be problem. Okay, so please try to understand. Sir, X relates to Y, X relates to Y, and Y relates to Z. Therefore, X should relate to Z is always true. If we call X as 1, Y as 1, and Z also as 1, then X relates to Y, Y also relates to Z, X also relates to Z. That will be the same thing. You don't need to worry about anything. Clear? So, please, you just need to understand there will be no problem in transitive relation. There will be no problem transitive relation because of presence of diagonal order pair. But in some cases, absence of diagonal order pair of some diagonal order pair there may be problem. Let's take an example of this. That in what cases there may be problem. Take relation R2. My question is, sir, 1, comma 2 belongs to relation and 2, comma 1 belongs to. What other order pair should be present? What other order pair should be present? So, sir, the idea is, sir, 1 belongs to 1, comma 2 belongs to relation, 2, comma 1 belongs to relation, then 1, comma 1 should also belong to relation. So it is missing. If we don't have 1, comma 1, if we don't have 1, comma 1, it will not be transitive. But if 1, comma 1 is present, then also will it be transitive? 1, comma 1 is present, then will it be transitive? 1, comma 2, 2, comma 1 will take you to 1, comma 1. 1, comma 2 will not have any problem with 1, comma 1. 2, comma 1 and 1, comma 1 will try to force you to add 2, comma 1, which is already present. But the problem is, sir, you only see in one direction. You only see in one direction. That is an unordered collection. So you can also check 2, comma 1 with respect to 1, comma 2. So another case is, sir, 2, comma 1 belongs to R. So we know 2, comma 1 belongs to R. 4, R2. 2, comma 1 belongs to R2 and 1, comma 2 also belongs to R2. Therefore, 2, comma 2 belong to R2. So, if 2, comma 1 belong to R2 and 1, comma 2 belong to R2, then 2, comma 2 should also belong to R2. But it is not present. But 2, comma 2 does not belong to R2. Therefore, not transitive. Make sense? But it is not the case only with respect to diagonal order pairs that the relation is not transitive. Sometimes because of absence of non-diagonal order pair also, the relation may not be transitive. So, relation R3. Okay, so let's see, if I say 1, 2, then I say 2, 3. Is this relation transitive? Is this relation transitive? No, sir, not transitive. Why? Not transitive. Because, not transitive. Because 1, comma 3 does not belong to R3. So, sir, is it the case that only the diagonal relation is the transitive relation, or only the relation which contains only the diagonal order pair is the transitive relation? No, I'm not saying so. Just need to be alert when checking for transitive relations. There are some ways, transitive closure, Warshall's algorithm, or you can do it manually. But let me give you an example with respect to this set, which is okay. So if I did 1, 1, 2, 2, and 4, 4, but not did 3, 3. Then I have added 1, 2, I have added 2, 1. So 1, 1 and 2, 2 are fine. Then I have added 2, 4, 4, 2. 4 and 4, 2 will take you to 2 and 4, 4. This is also fine. Then I have added, because 1, 2 and 2, 4, therefore 1, comma 4 should also be added and 4, comma 1 should also be present. So 1, 4 and 4, 1 will take you to 1, 1 and 4, 4. Now, please tell me, there is no order pair with respect to element 3, but is it still transitive relation? Yes, it is a transitive. Which one? R4. R4. Third transitive. So some other examples. Why only one? Some more. So let's say R5. Sir, what if condition itself is not true? So 1, 2 is present, but there is no order pair with true. Then 3, 2 is present, but there is no order pair. Then we have Is it a transitive relation? So 1 comma 2. So x comma y is present, but do we have any y comma z? Sir, there is no order pair starting from y, so no problem. So 3 comma 2 is present, but any order pair start with 2? No, sir. So this is also okay, this is also okay, is also a transitive relation. Please check the definition. That's the only thing which you need to do. Now, you may be thinking that, sir, you have given us the number of diagonal relation on set A, number of reflexive relation on set A, number of irreflexive relation on set A, number of symmetric relation on set A, number of antisymmetric relation on set A, number of asymmetric relation on set A. Do we also define number of transitive relation on set A? No, sir, we do not define. We cannot generalize in a single term, or we cannot generalize in the normal term of n for the transitive relations. So please do not generalize number of transitive relation on set A. Where mod A equals to n. So we do not generalize this. I mean, even if you do it, it will be a type of recurrence relation which will be very complicated to handle. But anyway, we do not generalize the transitive relation, number of transitive relations. Okay, sir. So, sir, what was the case? We started with types of relation. Started with types of relation. We have covered. We have covered in the last class. Done. Oh, we have done in the last class. We are done with the symmetric relation, antisymmetric relation, asymmetric relation, transitive. Now, in the last class, I told you that these are the relations which are formed on set A. These three are the relations which are formed on set A, that is from set A to set A itself. But these two relations, complement of a relation and inverse of a relation, can be from any set A to any other set B. There is no problem. Okay. So let's look at the complement. Let's look at the complement of a relation. Sir, complement of a relation. Now we know complement is defined with respect to universal set. When we were discussing the set operation, that is complement operation, we discussed that complement can be defined only for universal set, only with respect to universal set. So, sir, let's try to understand. Let R is a relation from set A to set B. It can be from any set to any set. Let R is a relation from set A to set B. Then complement of relation R complement of R can be denoted by various ways. Sir, I can write R bar, I can write R dash, I can write R complement, etc. And it is defined as, sir, how do we define the complement of a relation? Sir, how do we define the complement of a set? So how do we define? Let's assume that this is your universal set. This is your set A. Sir, how do we define complement? Sir, complement is defined. Sir, all the elements of universal set except the element of set. So it is basically nothing but U minus A. A complement is nothing but U minus A. In the similar manner, how do we define the complement? And it is defined as, so how do we define R complement? Sir, R complement. Sir, R is actually a relation which is derived from A cross B, because it is a relation from A to B. So this A cross B is the universal set. This universal set with respect to a relation from A. So all the order pairs of A cross B, all the order pairs of A cross B except the order pair of relation R. All the order pair of A cross B except the order pair of relation R will form the complement of relation R. Will form the complement of relation R. Clear? This problem. I hope you have understood this. Makes sense? So there will be a unique complement for any relation, so don't worry about that. Okay? So the next one is inverse of a relation. Next one is inverse of a relation. How do we define the inverse of a given relation? So just like inverse function need not exist all the time, but inverse relation will always exist. Inverse function will exist only if your function is 1, 1 as well as 1, 2. That is it is a bijective function. But for inverse of a relation to exist, there is no such constraint. Inverse of a relation will always exist. Inverse of a relation will always exist. Just note down. Let R be a relation from set A to set B. R be a relation from set A to set B. First of all, let us have the visual understanding of relation. So this is my set A, my set B. Right. Let's assume I have element 1, 2, then I have element A. Let's assume that the relation R from A to B is defined as that 1 is related to B, 1 is related to A, and 4 is related to this. So what will be R? Sir, R will be nothing but 1 relates to B, 1 relates to C, 3 relates to A, and 4 relates to B. Yes, sir. So this is my relation R. Now, if I try to define the inverse of a relation, then inverse of a relation will be nothing, but will simply invert the order pair of relation R. That is, it will become B, 1, become C, 1, become A, 3, become B, 4. So please try to understand if in a relation, if the first order pair is from relation B, then this will be a relation R inverse will be a relation from B to A, because in a relation within the order pair, the first element will be from the first set and the second element will be from the second set. So, sir, the first set has to be B, it will become ABC, and the next set will be A, and there will be element 1, 2, 4. So, what will be the matching, sir? A will relate with 3. A will relate with 3. What about B? So, B will relate with 1. B will also relate with 4. What about with C? So, C will only relate with. So, that's your relation. So, if you try to understand that what is an inverse relation, so it always exists. There is no such restriction that certain conditions should be satisfied like function. It will always be an inverse relation. Let R be a relation from set A to set B. Then inverse of relation R is a relation from set B to set A, and it is defined as, how do we define? It is defined as that R inverse will be a relation with a set that will contain the order pair B, A. It will contain all the order pairs of type B, A such that the order pair A, B belong to relation R. So if any order pair A, B belong to relation R, then its inverted order pair B, A will be present in relation R inverse. So all the order pairs which are present in relation R will be inverted and they will be present in the inverse of relation R. Clear? So that's just one definition. Next thing is that can we composite two relation, that is, can we define the composite of two relation, that is, can we combine two different relation and create a new relation So it may be possible in specific case. Let's assume that if I have a relation R1 which is from set A. So let me first define the concept and then I'll give you the definition. So this is set B. So R1 is a relation from A to B. Okay. Take any elements. One, just to understand. A1, B2, B4. So B1 not needed. Number of elements. B set need not be seen. So this is a relation R1. What does it say? Let's say the order pairs are of type that A1 relates with B1, A1 relates with B2. A2 relates with B1, A2 also relates with B2, A3 relates with B, and A1 relates with B2. Okay, that's perfectly fine. This is my relation R1. I hope you understand that the order pairs, how many order pairs? 1, 2, 3, 4, 5, 6 order pairs are present in the relation R1. Now, there is a common set B, and a relation R2 is present from this set B to a new set C. This C may be anything. So let's assume that this is your set C and the elements of this set are, let's assume C1, C2, C4. Does not matter how many elements are there, so please don't bother about that. Okay, sir, now please tell me that in relation R2 there will be some order pair. So let's assume that B1 is related with C3, B2 is related with C1 only, B1 is related with C4 also, and B3 is related with C3 is related with C2 only. So this is a relation R1. What you see here in this red color circle is your relation. Come on. This is your relation R1. And what you see is blue. Come on. Blue color circle is your relation R2. Now, the composite of R1 and R2, is denoted by R1, R2 or R1, R2. These are the notations. Sir, some author also uses R1 of R2. But this is ambiguous. Why? Because what is defined by some author as R1 of R2 is defined by some author as R2 of R1. So there's an ambiguity. Therefore, GATE will never ask you. I mean, I don't think that GATE will ask a question related to composite of two relations by defining it as R1 of R2 or R2 of R1, because they themselves know that there are two different types of definition for R1 of R2, right? So one book that defines R1 of R2 in a certain way, that same thing is defined by some other authors as R2 of R1. So that's an ambiguity. Therefore, more unambiguous notation is used to represent composite of two relations, that is R1 and R2, and that is R1 R2 or R1 of R2. So what happens in R1 of R2? So please try to understand. So R1 is a relation from A to B, R2 is a relation from B to C, then R1 R2 will be a relation from A to C. R1 R2 will be a relation from A to C. So what will be the type of relation? This is your A. This is your this is your set A. This is your set C. That means in this composite of R1 and R2, the element of set A, that is A1, A2, A3, A4, will relate with C1, C2, C3, C4, C5. So, sir, how exactly they are related? So please try to understand. The bridge, the set B will behave as a bridge. So there is an element B1. So let's look at one by one. Sir, A1 relates with B2. Sir, A1 relates with B2 and B2 relates with C1. Then A1 is related to C1 via B2. A1 is related to C1 via B2. Similarly, A1 also relate with B3 and B3 relates with C2. So A1 is also related with C2 via B3. A1 is also related with C2 via B3. So, sir, we are done with all the order pairs of all the edges with respect to A1. Let's look at A2. Sir, A2 relates with B1 and B1 relates with two elements. So, sir, A2 relates with B1 and B1 relates with C3. Therefore, A2 will relate with C3. A2 will relate with C3 via B1 and A2 relates with B1 and B1 also relate with C4. Therefore, A2 will relate with C4 also via B1. So, this bridge will take you to two different nodes of set C with respect to A2. Now what? Sir, A2 also relates with B2. Sir, A2 also relates with B2 and B2 relates with C1. So, A2 will relate with C1 also. A2 will relate with C1 also via this node B2. No. Yeah, via this node B2. Clear? Okay. Sir, let's look at A3. Sir, A3 relates with B2 and B2 relates with C1. Therefore, A3 will relate with C1. A3 will relate with C1. A3 will relate with C1. Now, sir, what? Okay. Sir, A4 relates with B4. Again, A4 relates with B2 and B2 relates with C1. Therefore, A4 will also relate with C1 via B2. Sir, we are done with all the order pairs. Sir, obviously 1, 2, 3, 4, 5. I mean, it's not necessary because some of them may be repeated. Some of them may be repeated. So it's perfectly fine. But the order pair will appear only once. Order pair will appear only once. So what's the idea? Sir, if you are trying to define the composite of two relations R1 and R2, then there should be a common set. And R1 is defined from A to B, then R2 should be defined from B to C. And then in that case, R1, R2 will be defined from set A to set B, and B will work as a bridge for that composite relation from set A to set C. Yeah. If I just want to give you the definition, which is a clumsy definition for the same thing that I explained on the previous slide. So, will be just try to understand this. That will be enough. So, let x and y, x, y and z be three sets. So, I'm just trying to define rather than A, B, C, we are using x, y, z. So, let's assume x is one set, y is another set, z is another set. Now it is saying that R is a subset of x cross y. So whatever is a subset of x cross y will be a relation from x to y. So R will be a relation from x to y. Similarly, S is a subset of y cross z. That is, whatever is a subset of y cross z will be a relation from y to z. So this S is a relation. S is a relation from y to z. Then it says, so these are two binary relations that is on two different sets. Then their composition, so it is denoted using this R composite S, or some author may also write it as R of S, RS simply. Okay. So then their composition is the relation defined as, sir, how do we define the composite relation? So then their composition is a relation defined as that R composite S will have the order pair x comma z, will have the order pair x comma z such that x comma z will belong to x cross z. So x cross z means it will be a relation from x to z. It will be R composite S will be a relation from x to z because this order pair belongs to x cross z. Therefore, R composite S has to be a relation from x to z. And when exactly this x comma z will be present, x comma z will be present in the relation, composite relation, if there exists an element y, if there exists a common element y such that x relates with y and y relates with z. So if x relates with y and y relates with z, then x will relate with z in this composite relation R composite S. So if there exists an element y such that x comma y belongs to R, that is x relates to y with respect to relation R, and y comma z belong to x, that is y relates to z with respect to relation S. If there is any such common element y which is working as a bridge for two elements x and z of sets x and z, if there is any element y which is working as a bridge for the element x and z of sets capital X and capital Z, then x comma z will belong to R. Exact same definition that I explained on the previous slide. So the simple concept is that what is R composite S? Sir, If R is a relation from X to Y, S is a relation from Y to Z, then R composite S is a relation from X to Z such that there exists an element such that order pair X comma Z will belong to this composite relation only if there exists an element Y such that X comma Y belong to R and Y comma Z belongs to S. That is, there is a bridge for the element X and Z, and that bridge is present in set Y. Clear? So whether you think of it in this particular definition or whatever I have explained the previous slide is up to you. So it's nothing but R. So this is the same definition. Don't think that these are two different definitions. These are not two different definitions. So I can say or this. Or this means another way of writing the same thing. So what is this? R composite S will be a relation from X to Z, and it is defined by the rule that X comma Z will belong to R composite S if and only if there exists an element Y belonging to Y such that X comma Y belong to R and Y comma Z belong to S. If there is any element Y, so this should be common. This Y should be common. X to Y and Y to Z, then X will relate to Z in the composite of R and S. So simple. So this is the composite of two relations. This is the composite of two. So I hope you understand that we have spent too much time in understanding the different types of relations. So in today's class, I'll only give you. So it's not so that I'll not complete the topic. So in today's class, I'll only give you the definition of equivalence relation. I'll give you the definition of equivalence class. I'll give you the definition of partition. But other thing related to those things will be dealt in the next class, that is in the tomorrow's class. So anyway, let's move to the equivalence relation. Sir, whatever we discussed till now were the basic types of relations. Basic means they have their own property. But now there will be different types of relation like equivalence relation, comparability relation, partial order relation. What are they? Sir, basically two or more basic type of relations will be combined. Two or more basic types of relations will be combined to create a new type of relation. So what is equivalence relation? So equivalence relation is a relation which is reflexive as well as symmetric as well as transitive. Clear? So whenever you are looking for equivalence relation, you need to check for three different properties. You must know reflexivity, you must know symmetricity, you must know transitivity. If all three properties are satisfied in a particular relation, then that particular relation will be called equivalence relation. So just note down the definition, it will be okay. A relation R on set A, again, because those properties reflexive, symmetric and transitivity are defined on the set which are defined from same set to same set. Therefore, equivalence relation will also be a relation from set A to set A, that is on set A. So, a relation R on set A, a relation R on set A is called an equivalence relation if and only if relation R, if and only if R is first reflexive, R has to be reflexive and symmetric and transitive. Reflexive, symmetric and transitive. This is what a equivalence relation is. So let's look at this. Let A equals to 1, 2, 3. Okay. Now the very first relation R1. Okay. Let's write it delta A. Delta A will be 1, 1 on what happened? 1, 1, 2, 2, 3. Please check whether it is reflexive or not. Yes, sir. All the diagonal order pairs are present, so it is reflexive. 1 comma 1 is present, symmetric pair 1 comma 1 is present. 2 comma 2 is present, symmetric pair 2 comma 2 is present. 3 comma 3 is present, symmetric pair 3 comma 3 is also present. So it is symmetric also. Is it also transitive? 1 comma 1 and 1 comma 1 will take you to 1 comma 1. 2 comma 2 and 2 comma 2 will take you to 2 comma 2. 3 comma 3 and 3 comma 3 will take you to 3 comma 3 also. So this delta A is the smallest equivalence relation on set A. So what is this? Delta A is the smallest equivalence relation on set A. Okay, another is A cross A. Please, sir, A cross A will be reflexive. Yes, sir, all the diagonal order pairs will be present. Will it be symmetric? Sir, if you look at this A cross A, you will realize, if you look at this A cross A, you will realize that in A cross A, for 2 comma 1, 1 comma 2 is present. For 3 comma 1, 1 comma 3 is also present. For 3 comma 2, 2 comma 3 is also present. So if you take all the order pairs of A cross A, then it will be reflexive, it will be symmetric, it will be transitive as well, because for two elements 1 2 and 2 3, if you need 1 3, then that order pair is also present in A cross A. Clear? So all the order pairs are present in A cross A. Therefore, transitivity property will also be satisfied in A cross A. So can I say that A cross A is the largest equivalence relation on set A? Is the largest equivalence on set A. Now your question may be, sir, is it the case that these are the only two equivalence relation on a set? No, sir, it's not. Sir, there may be. So first of all, it should be reflexive. So if you want to create any equivalence relation, first of all the diagonal order pairs should be present. Now, if you want to make it symmetric, then if you take 1 comma 2, then you should also take 2 comma 1. So is it a transit? Is it symmetric also? So 1 comma 1 is okay, 2 comma 2 is okay, 3 comma 3 is okay. Now with respect to 1 comma 2, 2 comma 1 is present, so it's fine. With respect to 2 comma 1, 1 comma 2 is present, so it's also fine. So now let's look for the transitivity. Diagonal order pair, presence of diagonal order pair will never create any problem because of transitivity. Now let's look for non-diagonal order pair. Sir, 1 2 and 2 2 will force you to add 2 2. 1 2 and 2 1 will force you to add 1 1. Nothing else starts from 2. Sir, 2 1 and 1 1 will force you to add 2 1. So it's already there. 2 1 and 1 2. 2 1 and 1 2 will force you to add 2 comma 2. So you just need to check with respect to last element. So if it ends with 2, then you only need to compare with the order pairs which are starting from 2. If it ends with 1, then you only need to compare with the order pairs which are starting from 1. So I compared 1 comma 2 with 2 comma 2 and 2 comma 1. Similarly, I compared 2 comma 1 with 1 comma 1 and 1 comma 2. Nothing else needs to be compared. Clear? So it's also, sir, so this is reflexive, this is symmetric as well as transitive. No transitive property is being dissatisfied, therefore there's also is an equivalence relation on. There may be some other equivalence relation, but I'll not discuss about them in the today's class. Tomorrow, so don't worry, don't think that, sir, are we skipping anything? No, sir, we are not skipping anything. It's just that tomorrow we need to discuss the concept of partial order relation. So partial order relation is also a combination of three different types of relations. Sir, here it is reflexive, symmetric and transitive, whereas partial order relation will be reflexive, antisymmetric and transitive. So we'll discuss about partial order relations in the tomorrow's class. So along with those concepts, that is reflexive, symmetric and transitive, I'll also explain with respect to equivalence relation. So along with partial order relation, I'll also explain with respect to equivalence relation. Don't need to worry about that. I'll not skip anything. So it may be the case that what you are expecting the base session, you may not get all of that in the particular session, but ultimately you'll get it in the next session. I hope you know the reason that there was some pendency from the last, we had some pendency from the last class that is related to types of relation. Therefore, anyway, some more thing related to equivalence relation will be discussed in the next class. That will be all. Next is partition of a set. So what do I mean by partition of a set? What is partition of a set? So partition of a set A partition of a set A is subdivision of elements of set A is a subdivision of elements of set A into subdivision of elements of set A into non-empty subsets such that uh, every element of set A every of set A is present in exactly one subset. Partition of set A is nothing but subdivision of elements of set A into non-empty subsets. So you need to partition the set A into non-empty subsets such that every element of set A will be present in exactly one of those subsets. So the idea is all the elements should be present. So let's look at this. Note, if set A is divided, let's try to understand the definition. If set A is divided non-empty subsets, set A is divided into non-empty subsets. What are the subsets? Two non-empty subsets, A1, A2, A up to AK. Then a set containing all these subsets of set A then the set containing all the subsets A1, A1, then this set containing all the subsets A1, A2, A3 up to AK will be called a partition of set A will be called a partition of set A if and only if and only if what first the intersection of any two subsets among this A1, A2, A3 up to AK. If you take any two subsets AI and AJ, then AI intersection AJ should be equals to phi for all I comma j such that I is not equals to j. So if the set is not same, if you take any two distinct subsets, then their intersection must be phi. What does it mean? That no element of set A should be present in more than one set. No element, because if this is the case, that let's say assume if I say A1 is equals to 1 3 and A2 is equals to 3 5. Okay, now if I take the intersection, I'll get the answer as 3. But why exactly this is coming as 3? Because there is an element 3 which is present in more than one set. But what did we say? That every element should be present in exactly one set. No element can go in more than one set. No element can go in more than more set. That's what is being checked by this first condition, that ai intersection aj should be equals to pi for all I comma j such that I is not equals to j. Because if I is equals to j, if you take the intersection of a1 with a1, then obviously it will not be pi. We are not checking with the same subset, we are checking with respect to distinct subsets. Okay, that's one thing. That so it only says one thing, that the element should not be present in more than one subset. This has checked one thing, that element should not be present in more than one subset, but we also need to check that element is present in at least one subset, not more than at least one, will be exactly one. So second will be, and second is, if you take the union of all these subsets ai, where I vary from 1 to k, then the union of all these subsets should be equals to A. That means this subset should cover all the elements of set A. This subset should cover all the elements of set A. Then only the union of the subsets will be exactly equals to A, because if any element is missing, then the union will not be equals to A. If union is equals to A, then we have covered all the elements of set A, and no element is present in more than one set. That is, every element is present in exactly one set. That is, every element is present in exactly one set. So this is your definition that this is your definition that partition of a set A is subdivision of element into non-empty subsets, such that every element of set A is present in exactly one subset. So that's the, this is okay. So if I just give you an example, I just give you this. If I take the, if I take this 2, 3, 1, 4, 5, is it a partition? No, sir. Not a partition. This is not a partition of A. Not a partition of, because empty set cannot belong to non-empty set. We just said that non-empty set uh, belong to. I'm not saying it cannot be empty. Not belong to. Empty set cannot belong to. It itself can be empty, but it cannot belong to partition. Second is, let's assume it's non-empty, but if I say 1, 2, 3, 4, 4, 5. So is it a partition? Is it a partition? Not a partition. Because 4 is present in more than one set. Four is present in more than one set. Third definition, want to cross check. So 1, 2, 3, 5. Is it a partition, sir? Not a partition, because 4 is missing. Not a partition because 4 is not included in any subset. Four is not included any. Okay, so sir, 4. If I write something, sir, 1, 2, 3, 4, 5. Sir, is it a partition? Is it a partition? Let's say the intersection of these two is phi. Intersection of these two is phi, and if you take the union of these two subsets, you will get A is a partition of A. The partition of A. There may be more than one partition. So let's like, if I write something 1, 2, 3, 4, 5. Is it a partition? Yes, sir. It is also a partition. Why? Because if you take any two subsets and if you perform the intersection, it will be phi. If you take the union of all these subsets, you will get A. It is also a partition. Yeah. So you can actually see all of them are non-empty. All of them are non-empty, and every element of set A is present in exactly one subset. Therefore, this is a partition. Makes sense? Okay, sir. We are done with the partition of our set. Yes, I have the example here, so don't worry. So, your homework. The homework. The homework. Find the number of partitions of set A. Find the number of partitions of set A when first mod A equals to 0, second mod A equals to 1. That if there is no element in set A, then what will be the partition of set A? If there is exactly one element in set A, then how many partitions of set A? Third, if there are two elements in set A, then how many partitions will be there for set A? If number of elements are 3, then how many partitions will be there for set A? Sir, if mod A equals to 4, then how many partitions will be there for set A? So these are your homework. Don't think that these are the silly things, because if you get them, you can study from any source you like. Wikipedia is one of them. So if you want to understand the concept, you can read from any source that how many partitions for a set A, its cardinality is 0, and what are they? If how many partitions of set A if its cardinality is 1, and what are they? How many partitions of set A when the cardinality is 2, what are they? Now, why it is important? Because the number of partitions of a set will eventually define the number of equivalence relation on that set. So if the cardinality of set A is 2, then the number of equivalence relation on set A will be exactly same as number of partitions of set A if cardinality of set A is 2. So if cardinality of set A equals to 4, then number of equivalence relation on set A of cardinality 4 will be exactly same as number of partitions of set A of cardinality 4. So there is a one-to-one correspondence between number of partitions of a set and number of equivalence relation on a set. Clear? So equivalence class, that will also I'll define in the next class. Right? So there are certain things that I'll cover in the next class. That will be some more examples related to equivalence relation. For examples related to equivalence relation that I'll cover along with the partial order relation. When I'll give you the example of partial order relation, I'll also give you some of the examples of equivalence relation. Apart from that, we will try to understand that how many partitions will exist for a set as the size of the set varies. Then we'll understand the concept of equivalence class, and we'll see that how equivalence class can be used to create partition. And apart from that, we'll see the number of equivalence relation, and that I already said that the number of equivalence relation on a set will be exactly same. Number of equivalence relation on a set will be exactly same as number of partitions of that particular set. So please don't mind, I'm not skipping anything, but I'll cover all those things in the next session. That will be tomorrow at 4 p.m. There's no change in time as well, so you can join tomorrow at 4 p.m. and you will get this two concept. I have explained what is a partition, I have explained what is an equivalence relation, I have explained different types of relation, but equivalence class and number of equivalence relation, these two things are exactly based on the concept of number of partitions. Don't worry, you are not missing anything. We'll cover these two things in the next class. That will be all for this particular session. Thank you very much for joining. See you tomorrow at 4 p.m. Same channel, same time. team mentor. Good night. Take care. Keep learning.